Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 13, and we are going to discuss today about two concepts, that is of the local volumetric strain and local rotation. Okay. So, again we can think of our body in the reference configuration and it is getting deformed. Then as the body deforms, the total volume of the body of course changes, but locally also the volume changes, which means if you take a small part of the body and also track its volume change, then you will see that that is also changing, and different parts the volume change would be different. Therefore, we talk of local volumetric strain, and later on I will talk about what is the meaning of local rotation. Okay. So, let us begin with local volumetric strain. So, to obtain volumetric strain, we will have to think of three line elements at a point. So, for longitudinal strain we had one line element, for shear strain we had two line elements, but for volumetric strain we will have three line elements. Okay. So, that the parallelopiped formed by those three line elements gives you some volume. All right. Let us have a look at it. So, suppose I have this point x in the body, point x, and there are three line elements. Let us say they are delta x, then delta y and delta z, and then you can think of forming a parallelopipe using these three line elements. For example, this is one such parallelopipe. Okay. So, basically the sides are those three line elements delta x, delta y and delta z, and then that parallelopipe, you see it looks quite big, but you have to think that it is at the point big X. So, the sides are really small, so that the volume is also small, and again since we want the volumetric strain at the point, so we will shrink those three sides, so that the volume finally shrinks to the point x and we get the strain at that particular point. So, we then track what happens to this volume when it gets deformed. So, in the deformed configuration we have the point little x, and then those three line elements become delta small x, delta small y and delta small z. Okay. And then you can form the parallelopipe. Okay. So, here are the three sides, delta little x, delta little y and delta little z. So, what is the volume of this parallelopipe? If we know the three sides, then the volume simply turns out to be, let us say the undeformed volume is big V and it is simply the scalar triple product, which is delta x dot delta y cross product delta z. So, that is a scalar triple product. See, volume is a scalar quantity, all right. And similarly, in the deformed configuration, the volume would be, let us denote it by small v. So, that is delta little x dot with delta little y cross product delta little z. Okay. We can also talk more about scalar triple product. So, here for example, this cross product delta y cross delta z. So, it is the area vector, it is the area vector formed by delta y and delta z. So, you have delta y and delta z. So, there is a face whose sides are delta y and delta z, is not it? That is this side you see here, this side, that is delta y cross product delta z. So, that is the area, and then when you dot it with delta x, you basically get the volume. So, delta y cross delta z, it gives you the base area, and then dot with delta x. So, area dot with delta x gives you the height. So, base into height, that gives you the volume of the parallelepiped. Okay. And likewise, even in the deformed configuration, you can think of delta little y cross delta little z as being the face consisting of delta little y and delta z as its sides. Okay. All right. So, what is the volumetric strain then? So, if I denote volumetric strain by epsilon v, then volumetric strain is simply the change in volume divided by original volume. Okay. So, that becomes small v minus big V divided by big V, which is also small v by big V minus 1. And of course, here we want the volumetric strain at the point big X. So, we have to also take the limit. So, in this formula you have to apply the limit, the volume going to 0. So, you have to shrink the volume to the point x, so that you get the volumetric strain at the point x. Okay. So, the scalar triple product that we have here can also be realized as the determinant of a matrix. So, basically this big V, for example, that is delta big X dot product delta big Y cross delta big Z. So, we could also think of it as the determinant of a matrix whose 3 columns are delta big X, delta big Y and delta big Z. So, I simply form columns using delta big X, delta big Y and delta big Z. So, I get the matrix, and the determinant of this matrix also equals this scalar triple product. Okay. Now, what can we say about small v? So, small v is again delta little x dot delta little y cross delta little z. So, that is also the determinant of delta little x, delta little y and delta little z. and then we have to write delta little x in terms of delta big X, and we already know this, that delta little x is big F of delta big X plus the higher order term, is not it, which is big O of delta big X whole square. All right. So, we will drop this higher order term here, because it turns out it does not influence the volumetric strain. All right. So, we could then write it as determinant of big F into delta big X, then big F into delta big Y and big F into delta big Z. All right. So, we are not keeping the higher order term over here. Now comes the trick. Look at this matrix. The three columns are F delta x, F delta y and F delta z. So, this F, the deformation gradient tensor, is pre-multiplied with each of the three sides. And if you think of it carefully, we would also be able to write this as the matrix F times the matrix of delta big X, delta big Y and delta big Z. Okay. This single matrix has been converted into a product of two matrices, the matrix of big F multiplied by the matrix of delta big X, delta big Y and delta big Z. Can you see how they are related to each other? See, when you multiply two matrices, then the product matrix that you get, what is the column of the product matrix? So, let me do a side calculation here. So, suppose you have two matrices A into B, and then B has got those three columns and it is equal to C. Okay. So, this is A into B1, B2, B3, and that has to become C1, C2, C3, right, the three columns of C. Now, can you see that C1 is actually A times B1, is not it? The matrix A multiplied with the first column of big B simply gives you the first column of the product matrix. You can also do hand calculation and verify it, but essentially the first column of product matrix is matrix A times the first column of B matrix, which is B1. Okay. So, if we are convinced with this, then we can of course write that as determinant of F into the other matrix, but then we have a interesting property of determinant, that determinant of product of two matrices is same as the product of the determinant of the two matrices. So, we could also write this as determinant of F times determinant of this matrix delta big X, delta big Y and delta big Z. Okay. But this is really interesting now. See, we finally get this as determinant of big F into the original volume, is not it? That is the definition for original volume. So, that is big V. So, if I now have a look at what we have derived, then small v times big V is simply determinant of F, isn't it, determinant of the matrix F. And therefore, the epsilon V, the volumetric strain, then becomes determinant of the matrix F minus 1, right. Now, let us try to write down this big F in terms of the displacement. So, we know that big F is identity plus grad u, right. So, big F is identity plus gradient of u. So, in the matrix form, then what is it going to look like? So, the matrix of big F, say in the E1, E2, E3 coordinate system, is then equal to identity matrix, which has 1 on the diagonal and 0 in the off diagonal, plus the matrix of the displacement gradient, which finally becomes 1 plus del u 1 over del x 1, and then 1 plus del u 2 over del x 2, then 1 plus del u 3 over del x 3, those are the diagonals. So, you have 1 added to each of the diagonals, because you have an identity matrix here, and then the off diagonals, they are simply del u 1 by del x 2, then del u 1 by del x 3, and here we have del u 2 by del x 1, del u 2 by del x 3, del u 3 by del x 1, and del u 3 by del x 2. Okay, so, that is the matrix. So, what is the determinant of this matrix? So, we have to apply the determinant formula. So, you have to expand it, let us say in terms of the rows. So, what do you get, for example? So, determinant of big F would then be, if I expand in terms of the first row, it is 1 plus del u 1 by del x 1 times 1 plus del u 2 by del x 2 into 1 plus del u 3 by del x 3 minus del u 2 by del x 3 into del u 3 by del x 2. See, this corresponds to this entry multiplied by the cross multiplication of these two, is not it? And then you will have minus del u 1 by del x 2 into del u 2 by del x 1 into 1 plus del u 3 by del x 3 minus del u 2 by del x 3 into del u 3 by del x 1. And where is this coming from? This is coming from this entry multiplied with the cross product of these two, the cross multiplication of these two arrows. Likewise, you will also get for the third one, is not it, which would be this entry into the cross multiplication of these two, right. So, finally, when you work everything out, what you will get is it is equal to 1 plus del u 1 by del x 1 plus del u 2 by del x 2 plus del u 3 by del x 3 plus the quadratic combinations or the higher order combinations of the displacement gradient. So, I will write here they are higher order terms, because what we get here is the quadratic and higher order combinations. And as in this class we are focusing on displacements such that the displacement gradient is very small. So, del u 1 by del x 1 or del u 2 by del x 1, del u 3 by del x 1, each of those components are really small. So, their quadratic combinations will be even smaller, right. So, we can neglect the higher order term. Okay. So, basically we get rid of this, and then up to linear order in the displacement gradient we have the formula already with us, right. So, whenever you have small displacements, we try to get the expressions which are linear in displacement, because the higher order terms will be negligible, is not it. All right. So, epsilon v is simply determinant of f minus 1. So, this is del u 1 by del x 1 plus del u 2 by del x 2 plus del u 3 by del x 3. Okay. So, that is the formula for the volumetric strain. All right. And you can notice that the right hand side is actually also equal to trace of the displacement gradient tensor. What is trace? So, trace is the sum of the diagonals, is not it? You remember the first invariant of the stress matrix, we were doing the sum of the diagonals. So, here we have the displacement gradient tensor and its matrix form. When you sum the diagonals, that is what you have here. So, it is the trace of the displacement gradient. So, volumetric strain is trace of displacement gradient, which you could also write as trace of half of grad u plus grad u transpose, is not it, because grad u, the trace of grad u is same as trace of grad u transpose. When you transpose, the diagonals do not change. So, trace of grad u will be same as trace of grad u transpose. So, when you add them, you have to divide by 2, is not it. All right. But the last expression tells me lot of things. Can you recall the formula for each of the strains? Let us recall them. So, the longitudinal strain epsilon, suppose it is n n. So, it is at the point big X and in the direction of line element n. So, that turned out to be half of grad u plus grad u transpose into n and then dot with n, right. Similarly, the shear strain, which we will denote by gamma and say m n. So, gamma m n at a point big X comma n comma m. So, the two perpendicular line elements are directed along n and m, and that turned out to be 2 times half of grad u plus grad u transpose into n dot with m. Okay. So, that is the shear strain, And finally, the volumetric strain epsilon v, let us say, at a point big X is simply the trace of half of grad u plus grad u transpose. Notice that the volumetric strain only depends on the point, it does not depend on what line elements we chose. So, the 3 line elements that we chose, delta big X, delta big Y, delta big Z, it finally drops out of the final expression, is not it? So, the volumetric strain for a point is unique. The longitudinal strain at a point depends on what line elements we choose, likewise for the shear strain, but the volumetric strain is independent of what line elements we choose. So, we can also write that here. So, this is independent of the 3 line elements. But another thing to notice on the right hand side, you see in each of the expressions we have this tensor half of grad u plus grad u transpose. So, that is the symmetric part of displacement gradient, is not it? So, we can give it a name. So, that is actually also called the strain tensor. Okay. So, we can write it as epsilon with 2 tildes. So, it is the strain tensor. So, we define it as half of grad u plus grad u transpose. Okay. So, it is the symmetric part of displacement gradient. So, we can write this, it is the symmetric part of displacement gradient tensor. And if you want to write in the component form, what do you get? So, epsilon I j, the matrix of epsilon tensor, epsilon I j will then be half of del u I over del x j plus the transpose, therefore, it is del u j over del x I. Okay, so, that is the component form. All right. So, this is about the strains, and we see that it depends on the symmetric part of the displacement gradient. Okay, having discussed the strain, we will now talk about the local rotation tensor. All right. Okay. So, let me again draw the 2 pictures, the undeformed and deformed body. And we are at a point big X, which gets mapped to a point small x here, and at the point big X there are so many line elements. Let us say this line element, which is delta big X, which gets mapped to delta small x, and we know that delta small x equals big F times delta big X. So, can you see that any undeformed line element can simply be mapped to the deformed line element by multiplying it with the deformation gradient tensor, is not it? We have of course dropped the higher order term here. So, let us forget about that. So, if the line elements are very small, then the deformed and undeformed line elements are simply related through the deformation gradient tensor at that point big X. All right. Now, let us write down this big F in terms of displacement gradient. So, big F is identity plus grad u, but we could write it as the symmetric part of grad u plus the anti-symmetric part of grad u. Okay. So, that is basically identity plus the epsilon tensor plus let us say a W tensor, the anti-symmetric W tensor. So, delta little x is then epsilon tensor times delta big X plus identity plus W tensor times delta big X. Now, let us try to see what is the meaning of these two terms. See, at any point big X there are so many line elements passing through that point. So, you can think of a small neighborhood around the point big X. So, think of a small neighborhood around the point big X, and there are many line elements here. So, what does big F do to line elements in this small neighborhood? So, from the formula that we have in the bottom, you see the first term is epsilon times delta big X, and epsilon is the strain tensor. So, the first term is basically responsible to strain the neighborhood of big X. So, you have several line elements around big X. The first term is responsible to generate strain. So, it generates longitudinal strain, shear strain, volumetric strain, everything is generated due to the first term here. So, this first term. If the epsilon tensor at a point is 0, suppose that the displacement is such that the epsilon tensor becomes 0, then there will be no strain in the neighborhood of big X. So, in the small part of the body around big X, there will be no longitudinal strain, no shear strain, no volumetric strain if the epsilon tensor is 0. So, that is just the first part. What is the use of the second part? What does this second part do? So, it turns out that the second part is actually responsible for rotating the neighborhood. So, it is responsible for rotation of neighborhood around big X. So, you see basically at the point big X we have so many line elements, material lines. If epsilon is 0, but W is not 0, then those line elements simply get rigidly rotated in the deformed configuration without undergoing any strain. So, the line elements will not change their length, nor the angle between them will change, nor the volume of the neighborhood will change, but they will simply undergo rigid rotation. So, it acts like a rigid body, but just the neighborhood of point big X, a small neighborhood. Why do I say this? Is because you see this identity plus W which we will prove that it is corresponding to rotation, it varies from point to point. So, for a point big X, W would be something, because it is half of grad u minus grad u transpose. So, it is the antisymmetric part of displacement gradient. Now, as u is changing in the body, therefore, the displacement gradient will also change in the body, is not it? It will be different for different points in the body, and therefore, the antisymmetric part of the displacement gradient will also change in general. So, that means different points in the body have different rotation associated with them. So, it is slightly difficult to visualize. For a rigid body, if the body was rigid, every point undergoes same rotation, every part of the rigid body undergoes same rotation, but if it is a deformable body, that is not the case anymore. And what this analysis tells us is that we can think that every part of the deformable body undergoes its own rotation. So, as a whole it is not acting as a rigid body, but locally it is acting as a rigid body, provided the strain tensor is 0. So, if the strain tensor is not 0, then of course, locally the body is also deforming, but if the strain tensor is 0 locally, then the body around a small part of the body around big X simply undergoes rigid rotation. Okay. So, basically identity plus W, it does local rigid rotation of a small neighborhood around X. Furthermore, this local rigid rotation varies from point to point. So, it varies from point to point. So, this means different parts of the deformable body undergoes different rigid rotation if epsilon equals 0. So, the strain tensor is equal to 0. Okay. All right, but we have not yet proved that I plus W is indeed the rotation. So, let us try to do that. So, there is something called Rodriguez rotation formula. Rodriguez rotation formula, according to which if you prescribe the angle of rotation and the axis of rotation. So, suppose E is the axis of rotation and it is a unit vector, and theta denotes the angle of rotation about that axis of rotation. Then the rotation tensor corresponding to this axis of rotation and angle of rotation can be written as identity times cos theta plus the skew symmetric tensor formed by the axis of rotation vector A, okay, into sin theta plus A tensor product A into 1 minus cos theta. Okay, and here this is the skew symmetric tensor. Such that the axis of rotation A is equal to axial vector of this tensor A. Okay, so, this is the general formula for rotation, for finite rotation. Let us see what happens if the angle of rotation theta is very small. So, what if theta is very small? So, in that case cos theta, what is cos theta then equal to? It is 1 minus theta square by 2 plus theta 4 by 4 factorial plus dot dot dot, and sin theta would then be equal to theta minus theta cube over 3 factorial plus dot dot dot. Okay, that is a Taylor's expansion of cos theta and sin theta. And if we restrict ourselves to small rotation, so that means if we only keep the linear terms in theta, then we can approximate cos theta with simply 1 and sin theta with simply theta, is not it? Now, let us try to put this cos theta and sin theta in our formula for Rodriguez rotation matrix and see what happens. So, then small r of A comma theta is simply identity plus A, the skew symmetric A into theta plus A tensor product A into 1 minus 1. So, this actually drops out. So, the rotation, you see what does it become? An identity tensor plus theta times a skew symmetric tensor, and that is what we had, no, identity plus W, and W was a skew symmetric tensor. So, this is a mathematical proof that what we had, the antisymmetric part of displacement gradient, actually it corresponds to rotation, but small rotation. Okay, so, this is a mathematical proof that identity plus W can be visualized as small, or they also say infinitesimal, really small. Okay. All right, this was mathematical. Let us see an example for when we have rotation about E3 axis. Can you recall what was rotation matrix looking like? So, for rotation about E3 axis and by an angle theta, the rotation matrix had cos theta minus sin theta 0, sin theta cos theta 0 0 0 1, and then say that theta is much less than 1. So, it is very close to 0, very small. So, in that case what happens to rotation matrix? Cos theta becomes 1, sin theta becomes theta. So, it is minus theta 0 theta 1 0 0 0 1, which also equals 1 1 1 0 0 0 0 0 0 plus a skew symmetric tensor theta times 0 0 0 minus 1 1 0 0 0 0. So, you can see for the rotation about E3 axis, which we are very much familiar till now, if the rotation angle is very small, it indeed can be written as identity matrix plus theta times the skew symmetric matrix. What is the axial vector of this skew symmetric matrix? The axial vector, so you recall from the first class where we had the correspondence between a skew symmetric matrix and the axial vector. So, here it has only 1 2 and 2 1 component. So, in the axial vector it will have only the third component, whatever is missing. The first and second component of the axial vector will be 0 and only third component will be there, and therefore, the axial vector is 0 0 1 and which is actually the E3 axis, is not it. So, the axial vector is also equal to the axis of rotation, and theta here gives me the magnitude of rotation. So, everything falls out very nicely, right. So, coming back to our identity plus W, identity plus W. So, you will have some small w which would be axial of this big W, right. So, what will be the axis of rotation? So, axis of rotation is then simply this W vector divided by the magnitude of W, and what is the theta? The angle of rotation, that is simply the magnitude of W, is not it? All right. Finally, let us have some figures and see is it making sense. So, let us try to use E1, E2, E3 coordinate system and look at what is the W matrix going to look like. So, the W matrix in the E1, E2, E3 coordinate system, it is a skew symmetric matrix, right, half of grad U minus grad U transpose. So, of course, the diagonal is 0, and what about the off diagonal? So, the entry here, that is del u 1 by del x 2 minus del u 2 by del x 1, is not it. So, this is half of del u 1 by del x 2 minus del u 2 by del x 1. What will be the entry over here? That is half of del u 1 by del x 3 minus del u 3 by del x 1, and likewise what is the entry over here? That is half of del u 2 by del x 3 minus del u 3 by del x 2. Okay, so, that is the W matrix. So, what will be the axial vector then? So, the axial vector small w, what is that equal to? So, the third component of this axial vector will be formed by the first row and second column, right, the 1 2. The entry in the first row second column of the matrix, take the negative of it, that forms the third component. So, you have to go back to the first lecture and see the correspondence, how to get the axial vector. So, basically here we have negative of 1 2 entry. So, this becomes half of del u 2 over del x 1 minus del u 1 over del x 2, right. The second component is formed by the first row and third column, and we take it as it is. So, this is the second component. And what about the first component? So, the first component will be formed by the entry in the second row and third column, but with a minus sign, right. So, this entry here is same as this, but you have to put a negative sign also. Okay, so, that is how you can get the axial vector. And when you take the unit vector corresponding to this axial vector, so if you divide by the magnitude, you get the axis of rotation, and then the magnitude itself, that would be the angle of rotation, right, quite simple. Think of a simple example. So, let us think of an example where u 3 is 0. Okay. So, u 3 is 0 and u 1 and u 2 are only present, but u 1 is then the function of only x 1 and x 2. So, this is a specific example. Okay. In general, u 1 is a function of x 1 x 2 as well as x 3, but here let us think of an example where u 1 only depends on x 1 and x 2, and u 2 likewise also only depends on x 1 and x 2. Okay. So, in that case, what can you say about the strain matrix? So, the strain matrix epsilon, what does it become? So, on its diagonal we have del u 1 by del x 1, del u 2 by del x 2, and del u 3 by del x 3 is 0. So, we have del u 1 by del x 1, then del u 2 by del x 2, and this is 0. The off diagonal, so this is del u 2 by del x 1 plus del u 1 by del x 2 and half of it, and this entry is same as that entry. What about the 1 3 component of the epsilon matrix? So, that is del u 1 by del x 3, but u 1 does not depend on x 3. So, it is 0, and del u 3 by del x 1 and u 3 is 0. So, that is also 0. So, this is 0, this is also 0, this is also 0, and this is also 0. Okay. So, the epsilon matrix has got lots of 0 entries. It is basically a 2 by 2 non-zero matrix. Likewise, what can we say about the W, the axial vector W? Look at it here. The first component is del u 2 by del x 3 minus del u 3 by del x 2. So, that is 0, right, because u 2 does not depend on x 3 and u 3 is 0. Likewise, the second component is also 0 and it has got only the third component. Okay. So, we can write it here. So, it is 0 0 and this component is half of del u 2 by del x 1 minus del u1 by del x2, correct. All right. Let us see how this strain matrix and the rotation matrix acts on two line elements. So, since here u3 is 0 and u and u2 are only functions of x1 and x2. So, let us think of two line elements in the E1 E2 plane. Okay. This is delta x1 and that is let us say delta x2, the magnitudes, and it is along E1 direction, the other one is along E2. So, I could also write it here E1 and E2. So, we have two line elements, two material lines in the body, and we know this formula that delta small x is equal to epsilon times delta big X plus identity plus W into delta big X, right. So, we have broken down this f into delta big X into two components. So, maybe first we will have the epsilon acting on it, right, and then we will have rotation acting on it. What happens if only epsilon acts on it? So, let us just confine to what is happening to the rotation of the line elements. So, we know that the shear, what does shear do? It changes the angle between the two line elements, is not it? And the total shear in this case, what is gamma 1 2 in this case is 2 times epsilon 1 2, right. If we have E1 and E2, the change in angle is gamma 1 2, which is 2 times epsilon 1 2, and that is equal to del u1 by del x2 plus del u2 by del x1. So, basically the shear means each of the two lines rotate by half of this angle. So, that the total change in angle is this angle gamma 1 2. So, here each of the two lines rotate, and these two angles are half of del u1 by del x2 plus del u2 by del x1. You see the bottom line, the E1 line rotates anti-clockwise about E3 axis, whereas the E2 line rotates clockwise about the E3 axis. If you rotate both of them in the anti-clockwise direction, then you do not get any shear, right. If both of them rotate in the same direction, then the angle between them do not change, and that corresponds to rigid rotation. Shear means both of them have to rotate in two different directions, then only the angle can change, right. Okay. So, this is just a shear part and then the rotation part, correct. So, in the rotation part we have already seen here, look at this, what is the angle of rotation? So, that is the angle of rotation, right. So, we can write here that this is half of del u2 by del x1 minus del u1 by del x2. So, because it is a local rigid rotation, So, both the two line elements will rotate in the same direction. So, what happens to E 2 for example? So, the E 2 line element, what is the total rotation of E 2 line element? The rotation due to shear plus the local rigid rotation, right. So, that is half of del u 1 by del x 2 plus del u 2 by del x 1 plus half of del u 2 by del x 1 minus del u 1 by del x 2, and if you add it together it simply becomes del u 2 by del x 1. Sorry, this is for the E 1 line element. Okay. So, for E 1 line element, the E 1 line element total rotates by del u 2 by del x 1. Can we see what happens to E 2 line element? So, for E 2 line element, the rotation due to shear plus rigid rotation. You see, for E 2 line element the rotation due to shear is clockwise. So, it is with a negative sign. So, therefore, it would be minus half of del u 1 by del x 2 plus del u 2 by del x 1, and then the rigid rotation, and the rigid rotation is simply anti-clockwise, which is plus half of del u 2 by del x 1 minus del u 1 by del x 2. So, that is the total rotation of E 2 line element, and what does this become finally? So, that is minus del u 1 over del x 2, that is the total rotation of E 2 line element. And can you recall from the last class that indeed the E 1 line element was rotating by del u 2 by del x 1, and the E 2 line element was rotating by del u 1 by del x 2, but in the opposite direction. I mean, if I draw it here, so that is the initial orientation for E 1 and E 2, and then after deformation it would become something like this. So, what is the total rotation? What is this angle? That angle is nothing but this green line, this height divided by the base, right. And what is the height equal to? The height was the difference in the u 2 displacement, right. So, the height was, if you can recall, this was u 2 of big X plus delta x 1 E 1 minus u 2 of big X. So, u 2 of the tip point of this line minus u 2 of the vertex. So, that is the green line, the vertical green line, whereas the horizontal is simply delta x 1. So, what is the angle? So, the angle is then height by base, right. So, tan theta is height by base, but if theta is really small, tan theta is equal to theta. So, the angle is simply height by base, and which is then you can see it is delta u 2 by delta x 1, which is del u 2 by del x 1 in the positive direction. So, you can see here total rotation of E1 line element is del U2 by del x1, and that is something we also figured out here. So, we said that there are two components to it, one is rotation due to shear and then the rotation due to the local infinitesimal rotation. Add them together, you get simply del U2 by del x1. You can likewise also think for the E2 line element. Okay. So, I hope you got some idea about the strain, the three strains, longitudinal strain, shear strain, volumetric strain, and also this very important concept about the local infinitesimal rotation, right. So, all right. So, thank you very much and see you in the next class.